Very good morning to all of you. I'll begin. Previous session we were discussing power diode and then the switching characteristics of a power diode. Actually, we started off by looking at the reverse bias characteristics, and then we found that whenever the depletion layer actually touched the n-n plus interface, we named that diode as punch-through diode. Else, the diode was termed as non-punch-through diode. That was one point which we discussed in the previous session. And the second point was among non-punch-through and non-punch-through. For non-punch-through diodes, obviously the width of the n-minus layer should be broad. It must be thicker as compared to a punch-through diode. Resultantly, for the same reverse voltage, for the same voltage rating, non-punch-through diode will have a slightly higher voltage drop, slightly higher resistance of the n-minus layer, which would lead to it is just a slightly increased forward voltage drop across the diode. Resultantly, punch-through diodes are preferred. Those are the 2 points with regards to reverse bias characteristics. And then we discussed the switching characteristics, which consist of turn on and turn off duration. Turn on time duration consisted of 2 distinct time intervals. Time interval occurs because of the reverse bias, which has to be nullified, meaning the depletion layer would have been established when the diode was off. Now we are turning on the diode. Therefore, that reverse bias or the width of the depletion layer should be brought down to 0, and then the excess charge carriers should participate in conduction. So the time taken for nullifying the depletion layer, for bringing the depletion layer width to 0, and then for establishing the charge carriers, excess charge carriers, that will comprise of one time duration. Other time duration is required for setting up the double injection process and the conductivity modulation of the n-minus layer. So that will be the second time duration. We had named these two durations as T1 and T2 respectively, so that total on time will be T1 plus T2. Time for turn on of the diode. For turning on the diode, it is going to be T1 plus T2. That was the turn on characteristics. For turn off characteristics, the process is going to be exactly opposite, which means because there are excess charge carriers in the n-minus layer, firstly we have to remove those excess charge carriers, and they are removed by the applied reverse voltage. That applied reverse voltage will result in sweeping away. It is just absorbed or sweeping away of excess charge carriers. And in the process of sweeping out, the recombination of holes and electrons will naturally occur. Therefore, first time duration will be required for removing the excess charge carriers by carrier sweep out and recombination. Second time duration is required for establishing the depletion layer. The depletion layer should grow in thickness. For that, the applied reverse bias will need some time for the the depletion layer to grow in thickness. That will be the second time duration. Now, during both these time durations, that is carrier sweep out or removal of excess charge carriers and the growth of the depletion layer, the voltage across the diode will not change drastically. It will be equal to that forward voltage drop, similar, very closer to that forward voltage drop, as long as there are charge carriers in the n-minus drift region. So the third time duration is required for bringing the diode to its normal off state or to regain its blocking capability. That is the reverse voltage blocking capability. For that, it needs some time, during which the depletion layer would have fully grown in thickness, and that depletion layer will be ready to withstand the applied reverse voltage. During the third time duration only, voltage across the diode will be reversed. Fine. And once the depletion layer is fully grown, when the depletion layer is ready to take up the applied reverse voltage, at that instant, the forward current through the diode will be 0, very close to 0. No leakage will be there, or if at all any leakage is there, it will be negligible. Leakage will be 0. And then the voltage applied across the diode will be reversed. We had named certain important parameters. IRR was termed as the reverse recovery current or peak reverse recovery current. VRR was the peak reverse recovery voltage, VR was the reverse voltage, TRR was the reverse recovery time. These are the features that we had come across. And the distinct feature between a power diode and a signal level diode is the peak overshoot during turn on. That is because of the stray inductance and the depletion layer capacitance which interact among themselves and then cause that peak ringing, peak voltage across the diode during turn on process. So that is the difference between a signal level diode and a power diode. These were the points that we had discussed in the previous session. Fine. Then I'll pass on to today's session, which will be on power transistors. I have shared my screen and I'm sure my screen is visible. As usual, we will discuss, as I was mentioning in the previous session also, we will be discussing the constructional detail or the structure of a power transistor. And then we will take up the VI characteristics, the operating principle along with the VI characteristics, followed by the switching profile. These are the 4 minor topics that we will be discussing for all power devices. Today we will take up power BJT. Now, the construction of a power BJT is like this. First of all, there will be a N plus substrate as usual. This is the substrate on top of which there is a N minus collector drift region. Please recollect this. I have been insisting on this drift region and its importance. That is the special layer that is available in all power electronic devices. So you need to focus on the drift region, its doping level and its thickness. Okay. So the substrate is going to be heavily doped, N plus, which means it is heavily doped, obviously. And the doping level is also typical doping levels are put up over here. It is going to be 10 power 19 donor impurities per cubic centimeter. And this forms the collector region. The substrate is going to act as the collector terminal. The thickness is going to be 250 micrometer. Typical thickness, it will be plus or minus definitely, depending on the voltage rating and current rating, but typical layer thickness are mentioned. And then comes the N minus drift region or layer, which serves as the collector drift region. It is sometimes called as the collector drift region as well. This is lightly doped. Obviously, you can again check that drift region will always be lightly doped. When you have light doping, depletion layer can penetrate inside. And only when depletion layer penetrates inside, the voltage blocking capability will be enhanced. So the drift layer should be lightly doped and it should be thick in size or wide because it has to support the growth of the depletion layer. Only then voltage rating, voltage blocking capability will occur. These are the 2 reasons. I am not writing this down because I want you to concentrate on the lecture, on my lecture, and then understand certain things. Fine. Now coming to the structure of a power BJT, we take a N plus heavily doped substrate, and then we grow a lightly doped collector drift region of sufficient thickness so that the voltage rating, required voltage rating is achieved. And then we have a moderately doped base is going to be moderately doped. You don't have any superscript, right? For the p-type layer, we take a p-type epitaxially grown layer of moderate doping density. Again, look at the thickness. Thickness is very, very thin actually. So base thickness is less as compared to the collector region and the drift region. The reasons we will discuss, and we take that forms the base layer, and then we will have a very thin emitter layer, which is again heavily doped. Emitter is heavily doped because that is where the charge carriers need to be emitted away from or starts conduction. Okay, so the structure that is shown over here is for an NPN transistor. This is even more popular. because the charge carriers, they are going to be easily mobile in an NPN transistor. Obviously, the symbol I need to draw, I do not know whether you people will be able to recollect. I will draw the symbol somewhere here. Anyway, it's always better if some sort of clarity is there. Whether you know or not, let me not presume. So this is the symbol of an NPN transistor. You will have the arrow mark pointing outwards. The terminals are going to be base, collector, and emitter. This is the symbol of an NPN transistor. PNP transistor will have the arrow mark in the emitter terminal pointing inward. That is going to be the PNP transistor configuration for you. But then the structure is going to be exactly similar, but for the layers, n plus, n minus, etc. So this is how the construction of a power BJT is going to be. Emitter, as I was mentioning, is going to be heavily doped. You can understand that by looking at the concentration level itself. So heavily doped emitter region. Now, let us understand why the base thickness should be less. When we try to understand this, that will actually take care of the operating principle as well. Now, operation wise, we will consider the classical signal level transistor alone without the N- layer. And we know that if we want to operate the BJT, the base emitter junction should be forward biased, while the collector base junction should be reverse biased. This is the way we operate the BJT. Remember, we are dealing with power electronics, so the amplifier characteristics, they need to be ignored. We don't want the amplifier characteristics. We want only the switching characteristics. So please remember that, which means active region should be avoided in the VI characteristics. Please have these things in mind and approach the power BJT operation with that background, with those things in mind. Now, as far as the understanding is concerned, we will take up the N- layer and then we will try to understand how the BJT operates and why the base thickness is deliberately made less. What are the consequences of having the base thickness or a thin base? Now, base emitter junction is forward biased as shown here, whereas collector base junction is going to be reverse biased. Now, you can understand that the voltage, actual voltage applied across the collector and VC and E. VCE will be VCE will be, I will name this as supply VS. VS minus the drop across the load. This load. Okay. So if you have current flowing through this, which is going to be the collector current, obviously, IC, and then obviously IC flows inside. IE flows outside, and then base current, again it will be inside. So you now have the actual relation IC plus IB is equal to IE, right? So basic governing equation also I will write IC plus IB is equal to IE. And then the normal signal level transistor, you might have come across this term. IC is approximately equal to IE. It will not be exactly similar because actually it will be IC is equal to IE minus IB, but then base current will be very, very small in a signal level transistor. In a power BJT also, the base current IB is small, which means the control variable is IB. Okay, control variable is less in magnitude. This is preferable. This is what we want in all controllable devices. This is a good feature. Okay, which means if you want to control the power BJT, you should not need a 10 ampere, 20 ampere current to control the 50 ampere BJT. No, it should not be like this. Just apply a milliampere IB and try to have control over that ampere range of collector current. That is what is expected. Fine. For that to happen, you need to have a reasonable amount of current gain. Current gain, can you tell the expression for current gain? I will write the symbol beta for a normal level, normal signal level BJT. I see. One more thing. Look at the width of the layers. Base current is just, base layer is just 20 micrometer in thickness, whereas collector layer is 250 micrometer in thickness. Where will charge carriers be more? Base is moderately doped, collector is heavily doped. Collector current will be extremely higher. So current gain is given by IC by IB. Of course, at constant VCE and etc. Now, if you want to have good control, you should have reasonable amount of current gain. Okay. Now, for that reasonable amount of current gain, base current should be small. For good current gain, I'll put beta. For good current gain, IB should be small. Now, if IB should be small, what should be the thickness of base layer? Please, simple questions. Less, that's all. If IB should be small, therefore, thickness of base layer should be small. Okay, that is one of the reasons for having a small, for having a thin base layer. Base should be, I should write base should be thin, not small. I will write thickness of base should be, I will put reduced, which means thin base. This is preferred. Now you look at this structure. I hope you can see the arrow mark, or I will use a highlighter, laser pointer rather. So now you look at this structure. If you have a thin base layer, fine. Now what will happen to the depletion layer? Where will the depletion layer grow? Under reverse bias condition, of course. Under reverse bias condition, the depletion layer has to penetrate into this n minus n plus interface. Now, when the base layer is actually very, very thin, then when a reverse voltage is applied, there is every possibility for shorting. Base is going to be shorted out if the base is very, very, very thin, very, very narrow. Under reverse bias condition, if the base is thin, base is going to be shorted out because the depletion will simply penetrate into the P layer and then it will touch the N plus P junction. So the flip side or the drawback of having a thin base is low voltage capability, low voltage blocking capability. Therefore, the thickness of base is actually a compromise. Fine. However, thin base layer means shorting out during reverse condition. Therefore, the base thickness is a compromise. I'll put trade-off between the voltage rating, voltage blocking capability and current gain. Okay, so trade-off between, I will write V rating and beta. I hope this is understandable. Very, very important point. As a result, the thickness of the base region. Therefore, now I should write current gain, not thickness. Therefore, beta of power BJT is less. It is somewhere in the range of 5 to 20. 5 to 20, we may think it is high, whereas when you compare it with the beta of a signal level BJT or a low power BJT compared to signal level BJT. Your classical semiconductor BJT, that is going to be in the range of 100. So compared to a signal level BJT, beta of a power BJT will be less because the base thickness is responsible for the voltage rating as well, indirectly. Fine. So if we have a thick base for a power BJT considering the voltage rating, then current gain will reduce. Fine. So we have to have a trade-off. That is what is being done. Otherwise, the operation is going to be exactly similar. You forward bias the base emitter junction, and then electrons will be emitted into the N plus layer because they are excess charge carriers. They are majority carriers. The electrons will actually cross this PN junction, N plus P junction, and then they enter into the base region. Base region, because it is thin, the electrons will easily be transferred to the N minus interface where we have a reverse bias that is applied. Therefore, these electrons will simply be pulled into the N minus N plus interface and then they cross over to the collector. As a result, we have establishment of the collector current. Electrons are flowing in that direction. Obviously, collector current will be in the opposite direction, opposite to the conventional electron flow. So this is how current is getting established in the power BJT during regular operation, during normal operation. When the supply voltage is increased beyond a particular value, now you may have to look at this. VC is supply minus load. So as load current IC keeps increasing, the drop V load keeps increasing. Therefore, the applied reverse bias keeps reducing. When reverse bias reduces, it means at one point the device is going to be forward biased. Right? The collector base junction will be forward biased at a particular value of IC. As a result, in power BJT, we will have what is called as quasi-saturation region in the VI characteristics of the quasi-saturation. This is another distinct feature which is available only in the power BJT. I repeat, as collector current increases, I will write the relation somewhere here. So collector current increases. When collector current increases, V load increases. When V load increases, the reverse bias applied at the collector base junction decreases. Fine. So remember, VCB is reverse biased. So when the reverse bias increases, it means it is equivalent to forward bias. So when collector base is forward bias, collector base junction, this and this, when it is forward bias, base emitter is already forward biased, collector base is also getting forward biased, Therefore, the BJT, when both the junctions are going to be forward biased, then it is going to be fully on. That is quasi-saturation. Okay. Beyond that, it gets into the secondary breakdown region or the hot saturation region. We call it as hot saturation. Secondary breakdown is going to be detrimental. So these are the features with regards to the operating principle of a power BJT. I'll stop or I'll pause for 1 or 2 minutes. I'll keep this slide. Okay. Now I'll display the characteristics, VI characteristics. This should look familiar to you, but for a few salient points, which are primary breakdown is one salient level or one salient region. Secondary breakdown is another. Quasi-saturation is the third one. Hot saturation is the fourth one. These are the 4 distinct features. About quasi-saturation, I spoke just now. And hot saturation is full drive. You can even call it as overdrive mode. I will write it here. Something like overdrive of the device. Overdrive, or the device is going to be fully on, fully turned on. That is hot saturation. Primary breakdown and secondary breakdown, these regions must be avoided. Because beyond this, beyond primary breakdown or secondary breakdown, the device is going to suffer from thermal runaway problem. What does that thermal runaway mean? When the device is subjected to higher voltage, very high voltage, primary breakdown occurs. That voltage level beyond which the device cannot withstand, that is called as, there are three voltage levels. One is BVSUS. This is called as sustainable maximum, sustainable voltage level. Okay, what voltage? Remember, we are looking at collector emitter and the collector current. Fine. So maximum sustainable collector emitter voltage. Now this is going to be a very, very important parameter. This in fact tells the voltage rating of the device at a particular value of a particular IC, which means the device is on when there is current flowing through the device. When we still have current flowing through the device, okay, you have IC for various values of base currents, the control parameter, you will have collector current flowing through the device. For a particular value of collector current, beyond a particular value of VCEO, if you try to turn off the device and apply that reverse voltage, no, the BJT cannot take it up. It will fail. That voltage is beta V sustainable. What voltage can be sustained at a particular level when the device is in operation? When the device is in cutoff, when it is not operating, then you have other two limits, BVCEO, when the base is open, when base current is open, and then you have other parameter BVCEO, okay, where the collector emitter region is going to be open. You don't have any collector current at all. So you slightly have a larger values. I will write those two parameters also. BVCEO, which is when IB equal to 0. Okay. And you have a case when base current is less than 0, or you reverse bias that base emitter junction, you can slightly extend this VCEO. Okay. But then practically we don't do that because that is a case when base current is 0, which means you simply apply voltage across the collector and emitter, and then you see what is the maximum voltage which the collector emitter junction can withstand. That is VCEO. Fine. Beyond that, you can't do anything. Base current is 0, which means it's not on. So this is one point. Secondary breakdown, primary breakdown, I have mentioned. Due to thermal runaway, one must avoid. Quasi saturation is a case when the collector emitter junction is beginning to get forward biased because of large collector current. You can understand that. Collector current magnitude is this. When large amount of collector current keeps flowing, the load voltage keeps increasing. Therefore, the applied reverse bias tends to become in quasi saturation. The applied reverse bias tends to become forward biased. Okay, at large IC values. Fine. That is quasi saturation. Beyond that, if you further increase the supply voltage, there will be even more higher amount of collector current. The device gets into hard saturation. That's all. That is going to be fully on. When the device is in hard saturations, BJT switch is on. BJT is on. When the device is in IB equal to 0, saturation, cutoff. IB equal to 0. Obviously, this is cutoff. Hard saturation is when full IC flows. The name is their saturation. So I will simply write it as on. This is off. Now, which are the two regions in which the BJT must be operated? Either in on or in off. It can be in hard saturation or it can be in cutoff. Active region should not be there. Okay. Reasons we discussed in the second session. In active region, you will have finite value of VCE, finite value of IC, product of which will be finite. So power dissipated across the BJT will be finite in active region, not preferred for power electronic applications. That's all. So active region is avoided considering the finite power dissipated across the BJT. Active region. Active region is avoided considering the power dissipated across the BJT, which is equal to VCE into IC. Right. Active region is avoided considering the power dissipated across the BJT, which is VCE into IC. That's all. This also I have indicated here. This is about the characteristics of the power BJT. Another 5 minutes. Now we know that we want to operate the BJT from cutoff to saturation. We want to bring the transistor from cutoff to saturation, turn on characteristics. Now for bringing the BJT, see the switching profile is going to be, firstly the BJT will be in cutoff. Gradually this cutoff should be brought into active mode. From active mode the BJT should get into quasi saturation, and then from quasi it should get into hard saturation. So there are going to be 3 or 4 time intervals. One is this cutoff IB equal to 0. Firstly, that has to be brought down to 0 first time, and then you have to establish positive base current second time duration, third time duration in positive, with positive base current. Make sure that the device is staying in the active region for some time, third time duration, and then make the device move into quasi saturation, fourth time duration. Finally, make sure that the device is entering into hard saturation, fifth time duration. So the turn on characteristics, turn on switching profile of a power BJT will contain these 5 distinct time durations, time intervals. All right. So I have indicated them. They are as follows. The first time duration, we are now discussing the turn on characteristics. I'm not writing anything because I have written the material, written the points over here. So the turn on characteristics, first and foremost thing that you need to understand is BJT is a controllable device. Base is the control terminal. Base current is the control variable. Collector emitter, they are the power terminals. So the characteristics will have the control variable and the power variable. Control variable is base current, but base current depends on the base emitter voltage that is applied. So you have IB and VBE. Power terminal is the collector emitter voltage, and the power is mainly because of the collector current that is flowing. So these 4 parameters have to be plotted for a BJT. Now, to turn on the BJT, initially the base emitter junction would have been reverse biased, so we need to forward bias that. So VBE was off, now it is forward biased. For that, there is this definite time delay TD on. So TD on is the time taken by the base emitter junction. Remember, base emitter junction is similar to a classical PN diode, N plus and P layer, that's all. So that will take some time for getting forward bias. That is TD on, first time interval. Now, after this first time interval, you will have the second time duration, which is going to be, the second time duration, during which now the base emitter junction is forward biased. Therefore, collector current can now start to grow. That is what is happening. Collector current begins to grow. When collector current begins to grow, at the end of TRI, we call this time duration as TRI, rise time TRI. Fine. So TRI is because obviously excess charge carriers have to be built up, have to be transmitted, or they have to be established in the N- layer. In the N- layer, it is here. Okay. So for that, it takes some time, which is the rise time. At the end of TRI, device will be in active region. Fine. Remember, till now, the voltage across the collector emitter has not fallen down. So try to recollect the characteristics. Active region VCE will be finite. Active region VCE will be finite. But for our BJT to be completely on, VCE should be less, ICE should be maximum. VCE should be less, IC should be maximum. I have repeated that. Now, so those two things will take some time. Those are the remaining two time intervals. The moment device is in active region, that has to be pushed into quasi-saturation. So for moving the device from active region to quasi-saturation region, there is some time duration because the voltage falls. We call it as fall time 1. TFV1, fall time 1. So during this time, TFV1, device moves from active region to quasi-saturation region. Finally, it will be complete when the device moves from quasi-saturation to hard saturation. Remember, the time taken from quasi to hard saturation will be more, voltage fall will be less. The slope of voltage will be less because it is very difficult to move. Already there are charge carriers which are established. So if you want to establish even more higher amount of charge carriers, the applied potential should be more. The base current should also be further increased. For that, it takes more time. So the change in voltage is going to be less. Therefore, slope is less. Therefore, more time is taken from quasi-saturation till hard saturation. That's all. So these are the time intervals. So total on time will be sum of all these things. Okay. And finally, after the device has entered into hard saturation, the voltage across the device will fall down and it will be equal to on-state voltage drop, which is VCE saturation. That's all. Okay. Now, this is the steady state on profile of the device. The device is in overdrive mode and it is completely on. Please understand this. The device is completely on when the BJT is in hard saturation, it is in overdrive mode or it is completely on. Please understand this. That's all. So these are the 4 time durations. Very quickly to recollect. Sorry. First time duration, TD on, is for forward biasing the base emitter junction. Secondly, from forward bias to active region. And then this is rise time. Fall time 1 from active region to quasi saturation. Fourth time duration, FB2. Fall time 2 will be from quasi saturation to hard saturation. That's all. These are the turn on characteristics, time durations. Now, physics of operation, what is happening with regards to the electrons, charge carriers, etc. You can refer textbook. I have put them in a nutshell. What is the process that is happening? Why the time durations are seen over here. One point. Another major point, turn off is exactly reverse of this. From hard saturation, the device must be brought down to quasi saturation. From quasi saturation, BJT to active. From active, you bring it down to cutoff. And then make sure that that reverse voltage, VCE reverse, is applied. So turn off process is exactly opposite to turn on mechanism. Fine. So that is the turn off mechanism. Therefore, I haven't put up the turn off characteristics. Of course, whatever I have said, I have summarized. I'm not reading this. Anyway, I'll be circulating the slide. And then turn off mechanism, just the reverse or opposite. That's all. So this is about BJT. I think I don't have anything else. Yes, fine. So I will stop with this.